Hello everyone, welcome to one of the last few videos of AP Physics C, Electricity and Magnetism. This is actually the penultimate video, the last but one. This is on magnetism, and our last video would be on electromagnetism, combining electricity and magnetism. And this is going to be the entirety of the unit. Pretty long unit, pretty complicated unit, one of the hardest in E&M, in my opinion. But yeah, without further ado, let's just get right into the content. So let's start with magnetic fields. Magnetic fields are kind of like electric fields in the sense that they are caused by charges. An electric field is caused by a stationary charge, and then you get those electric field lines that either point away, point towards, blah, blah, blah. For a magnetic field, it's caused by a moving charge, or another way to say that is it's caused by a current, and then there's like rings around it that are the magnetic fields. And so our most common example in everyday life is in a bar magnet, where there's north-south. You bring it to another bar magnet, north-south, and there's a magnetic field from north to south that gets created. It's a uniform magnetic field, kind of like a parallel plate capacitor for electric fields. So I might as well keep that there. Like how electric fields was E, and you'll notice in this video I'm gonna compare to electric fields and electricity a lot because they're very closely related. There's a lot of parallels between them, and so I'm gonna say like E is the symbol for electric field, B is the symbol for magnetic field. The formula for the electric field is the electric force divided by the charge. In other words, the electric force is equal to the charge times the electric field. In this case, the magnetic field is equal to the magnetic force divided by Q times V. And so another way you can write this is the magnetic force, the formula for it is Q times V, which is a vector, cross product B. So one difference is that you do care about the velocity in this formula, not in the previous formula though, not in electricity. So another way you can write this, if you don't know what cross product is just QVB, and the dot product is cosine, the cross product is sine theta. Now what's interesting about the cross product is that you have to take two vectors that are in a plane with each other, and the result would be perpendicular to both vectors. That is going to be the cross product. And so we use something called the right-hand rule to find out what the direction of the force would be. And the way it works is like this. You take your right hand, you point your forefingers in the direction of either the velocity or the magnetic field. It doesn't really matter. It's just velocity comes first in the equation, so I usually point in the direction of the velocity of the charge. And then you curl those the tips of your fingers towards the direction of the magnetic field. So, for an example, let's say the charge is moving up and the magnetic field is this way. Let's say there's a north magnet, south magnet here. Or a north pole, south pole. So you would have your fingers go upwards, and then you would curl them so that they face the direction of the magnetic field, and you find out what way your thumb is pointing. So this is a very terrible drawing of a hand, but it gets the point across. You whatever way your hand is oriented so that it's natural for your fingers to curl that way, you find the direction of the thumb, and that's going to be the direction of the force. So in this case, your hand is pointing straight forward, you curl it a little bit to the left, and that means your thumb must be pointing up, or like out of the page. If it was the other way, if you had to curl the other way, you would have to flip your hand over so that it would naturally curve. You can't like bend your hand backwards. Instead, you would go straight forward, curve to the right, and your thumb would be pointing down. And so that's the direction of the force. There's one little caveat though. When it's an electron, it's or a negative charge, it's the opposite. So you still do this right-hand rule, and you get the direction of the force. And if it's a negative charge on the object, you just flip the force. So in this case, let's say it was back to our original example again. It's going straight forward, curling to the left, force pointing upwards or out of the page. If it was a positive charge, then that would be it. If it's a negative charge, you would say force is actually down into the page. Because it's the opposite. Now, what am I saying about into the page, out of the page? Well, since in cross products we work with 3 dimensions, we're going to need more than just what's on our page. So there's up, down, or forward, backwards, depending on what way you're viewing it. I'm just going to say up, down, because on a flat piece of paper, it would be up and down, north, south. There's west, east, or sorry, east, west, or right, left. And there's out of the page, into the page. So that's where the third dimension comes in. The way we symbolize it is obviously up, down, right, left. Into the page is with the little X, out of the page is with the dot. The reason why is if you think of like an arrow, if you look at it coming towards you, you'll just see this dot over here. Usually it's dot with a circle around because that's how you'd actually see it if it was an actual arrow. But people just write the dot instead because you don't need that circle around it. If you look at it like an arrow, like a arrow going away from you, you just see the tail of it, which is usually like an X or like something weird like this, but we're just going to symbolize it with an X. So dot means out of the page, X means into the page. Just remember that. Okay, so that's mainly magnetic fields. It's just an overview. You need to do a lot more practice with right-hand rule and calculating it to actually get good at it. And we'll just do like 1 or 2 practice problems about that today because it's definitely not the hardest topic in this unit. So we're not going to focus our energy on that, but do a lot of practice on this because this is one of the basics. And if you get this down, a lot of the problems would become a bit easier. Also, that's not the only right-hand rule we're going to be talking about in this video, so be prepared to memorize a lot of different rules. Okay, a few applications of magnetic fields. So one of them is crossed fields where you have an electric field and a magnetic field. And there's 2 different types or 2 different applications. One of them is, I don't exactly know, like mass detection, mass spectroscopy, things like that. It covers a few different things, but the main thing is you have a particle and you accelerate it, so it comes in with some velocity, and you have an electric field. So in this case, let's say there's an electric field going downwards, which means you have like a parallel plate, for example. And that means this would be a plus, this would be a minus. So electric field going downwards, magnetic field going into the page with these X's we symbolize. Both of them are in the same area. What will happen to this particle? And let's say it's an electron, because this is what J.J. Thomson's experiment for detecting the, for measuring the mass to charge ratio of the electron was. So it's an electron, which means whatever force you get from the right-hand rule, you have to take the opposite of it. So electron, it actually works the same with the electric field too. If you think about it, electric field going downwards and an electron comes in, it has to go the opposite way because electric field is the way a positive test charge would go. So it's basically the same thing for right-hand rule. It's just a little bit more confusing. So electric field going downwards, electron going through, which means electric force, I'm going to use a different color, going upwards. For magnetic field, let's draw our little hand. Velocity this way, you curl it into the page, so like this, and thumb would have to naturally point upwards. But it's an electron, so it's going to be the opposite way. It's going to be downwards. And so these two should cancel off depending on like the velocity of the electron, but you can make sure that it cancels off by making the velocity of the electron perfectly enough to cancel it off. And I'll get to what I mean by that in a second. But basically, we know they're in opposite directions, and so the natural thing is, hey, let's try to cancel it off. You know, Fe should equal negative Fb, technically, but since we're only dealing with magnitudes for now, we can get rid of the negative sign. And Fe, we know, is Qe. Again, we're dealing with magnitudes, so it should be QV cross B, but since it's just magnitudes and they're perpendicular to each other, so this sine theta only matters if they're not perpendicular. So if it's something like that, then you would need the sine theta. If it's something like that, you don't need sine theta because sine of 90 degrees or pi over 2 is 1, so the sine theta doesn't even matter. So since these are perpendicular, perfectly into the page and perfectly down, and like perfectly to the right is the velocity. They don't matter. Charges cancel, and so you divide both sides by b, and you get the velocity is the electric field, the magnitude of the electric field divided by the magnitude of the magnetic field. So this is a pretty important formula to know. You shouldn't memorize it and like write it down as the first thing in an FRQ, but you should know how to derive it. And the way you derive it is just set the electric field and magnetic field equal to each other. So you would accelerate the electron with just enough speed, this exact value, so that it goes perfectly straight, because the forces cancel off. Now you might be wondering, what happens if the forces don't cancel off? So let's say it's too slow, right? If it's too slow, that means that velocity is less than what it should be, which means that either electric field is less than what it should be or magnetic field is greater than it should be. Either way, that means that there is more magnetic force than electric force. Magnetic force was this one, electric was this one, which means if it's too slow, it'll curve downwards. Magnetic force is greater, because greater, less, means smaller velocity. On the other hand, if it was too fast, if it was going too fast, then your electric field would be greater than your magnetic field, which means electric force would be greater than magnetic force. It would curl upwards, because this force is greater than that force. So that is the cross fields of this thing. Basically, when there's electric field and a magnetic field perpendicular to each other. That goes on to my next topic, which is just electrons in a magnetic field, like just electrons, nothing else. I'm actually gonna erase some of. I might keep that. I just want extra space. So, if you have a magnetic field, and for simplicity's sake, let's say it goes inside the page, and you have a charged particle, an electron, going this way, what's going to happen to it? So, you have a velocity this way, you are going into the page, so thumb points upwards, but it is an electron, so it would be downwards. So your force would be downwards. Oops, let's use a different color for that. Force would be downwards, velocity is straight forwards. So what happens is, after a little bit, it starts to, this becomes your new velocity. And what happens then? Well, your force would remain to be perpendicular to your velocity. That's how the cross product works. It's always, the result will always be perpendicular to your components. So it keeps going like that, and soon enough, you'll realize that it's just a circular path. We could have found that out initially, because we know velocity and acceleration, or force perpendicular to it, has to be centripetal force, because that doesn't change the magnitude of the velocity, it just changes the direction. And so what we found out is that if you just have a charged particle in a magnetic field, it's going to follow a circular path. It's because it continuously deflects the electron, or the charge. Now, what is the radius of that path? Well, you can figure that out. How? Because the centripetal force is the magnetic force, which means mv squared over r, that's the formula from like all the way back in mechanics, is equal to qvb. Again, they're perpendicular, we don't care about the sine theta or the cross product. One of the v's gets cancelled, so mv over r is equal to qb. So multiply both sides by r, mv is equal to qbr, divide by qb, because we want r, mv over qb is your formula for radius. Again, just like this, you should know it. You should know how to derive it, so that you don't just write it down immediately. You need to derive it from this, and then you'll get this, which is a handy equation when you're given like just a single charged particle, because sometimes you need to know the radius of the path, and if you know all this, you can figure out the radius. Sometimes you know the radius, you want to figure out how fast is it going, what is the strength of the magnetic field, things like that. And yeah, another application of this is the fact that mass affects the radius, and so you can, if you don't know what a certain particle or atom or something is, you can figure out its mass by sending it through with a known velocity. So you accelerate it with a potential difference to get a known velocity. You send it through a known magnetic field, and you know the charge of it too, because let's just say it's a new well, it'll be like a ion, for example, and you know the charge of the ion, you just don't know what its mass is, so you don't know the like the element it is. So going to chemistry for a second, all ions, like all singly charged ions, so just they have one electron extra, have the same charge, but they don't have the same mass, because the element has different mass. Each element has a different mass. And so let's say you know you have an element that has an extra electron, you just don't know what element, and so To figure that out, you send it through this. You know the velocity because you accelerate it as such. You know the magnetic field. You know the charge. You don't know the mass or the radius technically, but experimentally you can see that it curves in this way. So what you have to do is the magnetic field. I'm just drawing over my stuff, but you send it through a magnetic field so it has like a curved path. You measure the radius and you can plug it in to solve for the mass. So that's another thing they might ask you to do on an FRQ. Last application is the Hall effect, which I'm going to quickly go over. Is just when you have like a wire and you have a current going, let's say, downwards. That means the electrons are technically moving upwards because the conventional current is the opposite of which way the electrons go. If you have a magnetic field, let's say into the page, I know all of this is into the page, but it's just nice and easy to remember. Then velocity goes upwards, magnetic field goes into the page, and so which way do your thumbs go? Well, this way, because you have to hold it, that's how it naturally curls, and so it has to be the opposite, so the force is going to be this way. And so that means that in the wire, the electrons kind of curve towards the edge, which means this is going to have a more negative charge. This is going to have a positive charge on this side of the wire. And so there's going to be an electric field that runs through the wire now. And that's going to actually cancel the effect of the magnetic field. And so that's basically what the Hall effect is. There's this new potential difference that is generated by a magnetic field, which is pretty cool. All right. Moving on to our next topic, which is forces on current-carrying wires. So when you have a current, so like I said at the beginning, a charged particle, the movement of a charged particle causes a magnetic field. Now, there's two very different aspects of it. You can have the effect of a magnetic field on a current, and you can have the creation of a magnetic field by a current. And so we're going to be dealing with the first part here. You already have a magnetic field, and you just want to see how it impacts a wire or a current. So let's say into the page, I know I should probably vary it up at some point, but let's say you have a magnetic field that goes into the page and a current that goes, let's say, this way. That means that the electrons are going to be moving the opposite way. So they move backwards and into the page. So which way does your hand curl? Well, the thumb has to point down, which means basically the force is upwards because it's the opposite. And so your magnetic force is going to be FB this way. So whenever you have a magnetic field and a current running through it, or like a wire, the wire is going to actually bend. So if it's actually going to like physically bend upwards, and the formula for that is just FB is equal to the current times the length, cross product, the magnetic field. Now, why is there a cross product? Because length is actually a vector. The length vector has the magnitude of the length. So the magnitude of the vector is the length itself, and the direction is the direction of the conventional current. So in this case, the length vector would be this direction and a magnitude of L. So that's going to be your formula for magnetic force on a current-carrying wire. Now, if you have a curved wire, you can use an integral, because this only works if it's straight. If it's curved, it's equal to the integral of I dl cross B. So in this case, dl is an infinitesimal portion of the wire. And then you cross it with the magnetic field. So let's talk about the right-hand rule for this. It's exactly the same as what we did before, but now instead of thinking, hey, which way is the charged particle going, which way is the charged particles going? In this case, since it's electrons going the opposite direction of the current, you can actually think of it a different way and an easier way. That means that you're going to have to memorize two different rules, but I feel like if you can memorize it, then you probably should. Instead of saying electrons are moving this way, opposite the current that is given, and then you have to flip the sign later because it's electrons, you can just say, hey, conventional current is the direction that protons go, or like positive charges go. So what if I just assume that the positive charges move the direction of the current? So you go point your fingers in the direction of the current, you curl it into the magnetic field, and you don't have to flip the sign of the force that you get. In this case, if you go fingers to the current, curl it to the magnetic field, if points up, which is what we got of the magnetic force either way. So it basically stops you from doing two unnecessary steps. That means you do have to memorize a different rule, or I guess you don't have to memorize a different rule if you legitimately think that the positive charges are moving the direction of the current. So yeah, either you have to do it electrons or positive charges. You can do either that you want. All right, that was current carrying wires. We can also talk about loops. So if you have like a rectangular loop that is like held in place, for example, and you got a magnetic field, this time not into the page. So we are changing it up a bit. This is moving to the right, magnetic field to the right. Let's see. Current goes around this way. I'm going to use a different color. Current goes around this way. Which way is going to be the magnetic force? Well, it actually depends on which portion of the loop you're talking about. So that's color coded. This is 1, this is 2, this is 3, and this is 4. I don't know if you can really see the yellow, but portion 1. So current is going that way. And then you are curling your fingers that way. So it's like that. And which way does your thumb point? Down. And so the magnetic field force would be downwards. Let's look at number 2. Which way is the current going? Straight, like to the right. Which way is the magnetic field going? Also to the right. So which way do you curl your fingers? You actually don't. So when your magnetic field and your velocity or your current are in the same direction, there is no magnetic force. Because think about it. There's that sine theta, which we ignored before, but there's that sine theta in the expression, and if theta is 0, the angle between the vectors is 0. It's 0. Sine theta is 0. And so you're going to not have any magnetic force at all. For portion 3, current is going downwards. So it's going down, curling it to the right. So it's like that. Which way is that? That's going to be upwards. And so upwards. And 4 is the same thing as 2, where it's in the same direction, or it's in opposite directions in this case, because current's that way, magnetic field is that way. So it doesn't, it again cancels out. And so what you get here is that there's going to be a force upwards on one side, downwards on the other, and so it's actually going to torque. It's going to torque about, and that's basically what a electric motor is. This gets into dipoles. Dipoles are like coils that get a uniform magnetic field. And just like we had electric dipoles, we have magnetic dipoles. And so the magnetic dipole moment is mu, is equal to N-I-A. So I is the current in one portion of the loop, N is the number of loops there are, and A is the area, so the cross-sectional area. So I think this is on the equation sheet, so you don't have to memorize it. And then the torque that the dipole experiences is equal to this times B. Kind of like in electric fields where it's equal to the electric dipole moment times the electric field. You can also find the potential energy or the orientation energy of a magnetic dipole, and it's U of theta technically, because it's an angle at which it's rotating. That's equal to negative of the dipole moment times, not cross product actually, dot product times B. Because remember, a dot product gives you a scalar, and we want potential energy to be a scalar. So yeah, that's that. Moving on to the second major thing about magnetic fields is that current carrying wires can cause magnetic fields. I told you this earlier, where there's two different effects of magnetic fields or focuses: the effect that magnetic fields have on current carrying wires and the effect that current carrying wires have on magnetic fields. And so if you have a current carrying wire, current this way, it causes a magnetic field around it in like concentric circles. Which direction? Well, there's another right-hand rule for you to figure it out. In this case, you instead of like curling your fingers or whatever, you're gonna hug the wire. So take like a pencil in your hand, point it the direction of the current, so like pointy tip towards the current, and just grab it with your thumb pointing to the pointy tip. So a little drawing of it. So if you have your pencil that way, which is the direction the current's going, you just grab it with your right hand I cannot draw hands. Okay. Okay, that's the best I can do. So that's your pencil. You grab it with your right hand, and which way are your fingers curling? So before we were saying curl your fingers, which way is the thumb pointing? Now we're saying point your thumb in the direction of the current, which way are the fingers curling? And so we see that they're going to be curling like towards the outside of the page here. Because like if you just grab your pencil and you look at which way the fingers are at that specific point, it's going to be this way. If you like rotate your hand a little bit and grab it a different way, which is around here, you see that they're going to be pointing into the page basically at the other sections. That makes sense. It's basically going, in this case, it's going to be going counterclockwise. It's a weird perspective, but this is one of the hardest right-hand rules to actually draw. So I would suggest doing some practice with it yet again. It's just conceptual. It's not that hard once you do some practice, but it's hard to explain it. And so I would suggest doing some practice on that. Now we get onto actually like calculating the magnitude of the current or the magnetic field. And so if you don't have a straight segment, which you're not going to usually, whenever you use the law that I'm going to tell you about, you usually don't have straight segment. You have this curly segment, and so you can calculate the section, like an infinitesimally small section of the wire, and calculate the magnetic field around that. Before we do that, though, I do want to tell you about mu naught. So remember epsilon naught, the permittivity constant. Mu naught is the permeability constant, and that's equal to 4 pi times 10 to the power of negative 7, which is around 1.26 times 10 to the power of negative 6. Units are Teslas times meters per amps, which I actually didn't mention earlier. I should have. But Teslas are the unit of a magnetic field. Good to know. Yeah, I didn't really talk about units at all, did I? Teslas are magnetic field. Newtons are obviously magnetic force. And I think that's all the new values we learned about this unit. Okay, so yeah, that's mu naught. So the formula for this is, I'm not going to derive it. You can derive it. Like, it is possible to with like calculus and all that. I am not going to derive it. First of all, it takes like 10 minutes. Second of all, it's very complicated, and it's going to take like 20 minutes to even explain the math. And third of all, you don't need to on the AP exam. It's on the equation sheet. The formula is dB, like the infinitesimally small portion of the magnetic field generated, is equal to mu naught over 4 pi times the current in that small section times ds, cross product r over r squared. So what that means is r hat is just like the direction of the radius, or direction of the, yeah, basically the distance. So ds is this segment, ids is in the direction of the segment, the value of the current, and then r is basically the distance from this to the point you're measuring. So let's say that's the point you're measuring, then r would be towards that, and r hat would be just the direction towards that. R would be the entire distance. So that's basically what you have to do. If you don't want to write in vectors, you can just write in scalars, which is mu naught over 4 pi times ids times sine theta. So instead of r vector, you just times it by sine theta and still r squared in the denominator. So yeah, there's two forms of that. We will do a practice of it in the practice problems, but for now, you just need to know that. Now, a simpler form of this is if it's straight and infinitely long, the entire magnetic field, not just a portion of it, is equal to mu naught over 2 pi times the current over r. So yeah, that's also good to know. I do believe that's also on your equation sheet, if I remember correctly. But yeah, either way, good to know. So that's Biot-Savart. This is called the law of Biot-Savart. Spelled B-I-O-T S-A-V-A-R-T. Biot-Savart. And that's the main law, this. But there are variations of it. For example, if you have a circular arc. And so if you do have a circular arc, which is like that, your magnetic field is going to be equal to mu naught over 4 pi times the current times theta, which is the angle that the arc makes, over radius. Which, again, I'm not going to show you how to derive. I think there is a practice problem on it, though, so I'll show you how to use it in the practice. There's also, if you have two wires, you can calculate the force that one wire applies on the other. Because remember, wires create a magnetic field, and wires also feel the effects of a magnetic field. And so there's a formula for that. But first, conceptually, parallel wires that have currents in the same direction attract each other. Why? Let's look at an example. Let's say current are both this way. You use the first, this right-hand rule for the first wire. You put your thumb up, and you curl your fingers around. You want the magnetic field at this point. And so you put your pencil up, you curl it around, and you see that it's going to go into the page, new color, into the page at this point. Well, if the magnetic field is into the page, which you can denote with X's, we can use the other right-hand rule. We say current goes up, magnetic field goes into the page. Which way does the force point? Well, your thumb points this way. And so your magnetic force would be this way. And you can do the same thing for the second wire on the first wire, and you're going to get the magnetic force of that is also towards the other wire. So they're going to attract each other. Same currents, same direction of current attract each other, different direction of currents repel each other. You should know that. You should also know how to conceptualize that using right-hand rule. So what's the formula of it? The force of B on A is equal to mu naught over 2 pi times the length of each wire times the current of A times the current of B over D, which is the distance between them, the wire separation. So yeah, you should know that. It's not on the equation sheet, I don't think, and it's hard to derive it, so you should just know it in general. Actually, I think you can derive it with this. Or maybe... Yeah, I'm sure you can derive it with Biot-Savart, but you're not going to use that much. Another law that you need to know, first Biot-Savart, is also Ampere's law. And that basically says that the integral of B ds is equal to mu naught times the current enclosed. Does that look familiar? It should, because that's just the magnetic version of Gauss's law, which says that electric field times ds, dr, doesn't matter, is equal to mu naught, or epsilon naught, sorry, times Q enclosed. It's basically the same thing, but with magnetic terms instead of electric terms. And so, again, you should know this. It's on your equation sheet, and you should know how to use it. We do have an example of that in the practice problem, but quickly I'll say something called an Amperian loop. It's kind of like a Gaussian surface. An Amperian loop is just a loop, and the current within it is the enclosed current, and like you can current going out and current going in cancel each other, for example. We'll do an example problem on it, but yeah, you get the point. Fun to use that. Last topic for this unit is solenoids and toroids. A solenoid is like a loop, kind of like a slinky, but you know, with electric, with a current going through it. It also causes a magnetic field. That's just going to be the vector sum of the magnetic fields caused by each loop. And so if you take the cross section of the solenoid, where each of these is like a different coil, you find out that it's the magnetic field is going to be mu naught times the n, which is the number of coils, times I over h, where h is the length you're looking at. So h entirely depends on the cross section you're looking at, but we'll get to that in a second. The reason why this works is Ampere's law. If you just use it by looking at this cross section, you're gonna get this is gonna pop out immediately. Now, the reason why h, we don't like just looking at a value of h is because, well, you can take any cross-section, that's going to change. And so n over h is constant. The number of coils or loops per length. And that's denoted with the lowercase n. And so it's going to be mu naught times n times I. Is going to be the formula for the magnetic field generated by a solenoid. Now, what's a toroid? It's when you take a solenoid and you connect the ends together. So you get like a donut of loop. which is pretty cool. I like toroids. But how would you calculate the magnetic field generated by it? Amperian loop, Ampere's law. You're going to get B, where can I write this? B is equal to mu naught over 2 pi times IN over R. So in this case, a few differences. One, IN, same thing, IN here, but this is, N is the number of loops, not number of loops per length. And R, it actually depends on how far away you are. Solenoids, it actually doesn't depend on how far away you are. Anywhere within the solenoid, and you're going to feel the same magnetic field. In a toroid, though, it depends where you are relative to the center of the toroid, because that's actually going to change, like, if you have, like, a toroid here, the magnetic field at this point is not the same as the magnetic field at that point, because of that R in that term, which is interesting. Again, toroids, I prefer them over solenoids. But they're also harder to calculate for, so I guess it can kind of cancel that. All right, that's all for our content review. Hopefully that helped. It's a big unit, and I try to rush it a little bit because I don't want a very long video. So, yeah, hopefully the content review helped, but maybe there's a few more things that we can touch upon in the practice problems. So I have 6 practice problems, which is, I think, a bit less than usual, but some of these can be a bit time-taking. So let's get right into the first one. First one is simple one. It's just definition of magnetic field and magnetic force. It says, it gives us the magnetic field in Teslas, remember? It gives us charge and gives us velocity. We want to find, first of all, the sign of the particle, and second of all, magnetic force. So sign, we can use the right-hand rule. So magnetic field is upwards, vertically upwards. And okay, I'm going to use a common color scheme for this. Magnetic field, I'm going to give, let's say black, right? Magnetic field is black. Charge doesn't have direction. Velocity is going to be blue. So velocity is towards the east. And charge is 8.5, which we can just remember is 8.5 microcoulombs. So now this will help us find the magnetic force direction. It says magnetic force is, okay, I messed up a little bit. Okay, I'm going to redraw it. So the wording is a bit weird. Northward is the velocity. So velocity, I'm going to say northward. Vertically upward is weird. That just means it's going to be going out of the page. So that would be dots, because it's coming towards you, dots. Not into the page, like it usually is in my examples. So you can't say that there isn't a diversity of examples here. Okay. So magnetic field out of the page, velocity towards. It says that magnetic force then is towards the right, towards the east. So let's see, does that work? You point your fingers in the direction of velocity, which is like northward, upward. You curl your fingers out of the page, and your thumb points to the right, which makes sense. Yeah, so if you do curl it, so let me draw it for you. You point your fingers in the direction of the velocity, and you curl it upwards. Your thumb is going to have to point this way. That's your hand. And doesn't look like a hand, but that's your hand. Your thumb is going to be pointing to the right, and the force is pointing to the right, which means that it is positive. It's not a negative charge, in which case you would have to flip the sign of the thumb to get the force. It's going to be positive. Find the magnetic force of the particle. So this is the magnitude of it. So we use the formula FB is equal to QVB. The reason why I'm not worrying about the cross product is because all these are perpendicular to each other. East, north, and out of the page are exactly perpendicular to each other. East, north, out of the page. Perpendicular. Perfect. So you just plug in your value. So this is 8.5 microcoulombs. So 8.5 times 10 to the negative 6 coulombs. Velocity is 4.75 kilometers, so times 10 to the power of 3 meters per second. And B is 1.25 Teslas. So you multiply all those together, you're going to get 0.0505 newtons, approximately, is going to be your magnetic force. So yeah, that's that problem. Relatively simple problem. Moving on to the second one. This is a singly ionized, so one electron is removed. So it's going to have a positive charge. And it's accelerated and then passed through a velocity selector, consisting of perpendicular electric and magnetic fields. The electric field is 155. Okay. All right, so there's a few parts to this. Let's draw a little diagram, shall we? You got a particle. It's moving this way. Magnetic field is... I said black, right? Magnetic field is... Doesn't say, does it? Let's assume it's into the page. And let's say electric field. I didn't come up with the color for this. I'm just going to say it's purple. Electric field is going down. I think that works because if there's an electron, that means its magnetic, its electric force would be upwards. Let's do green for that. Electric force would be upwards, and magnetic force. So you put your thumb out. You put your fingers out forward or to the right. You curl them in. And so your thumb is going to be pointing upwards. It's an electron though, so you reverse it, which means that your magnetic force is indeed going to be downward. So they do cancel off, just as we expect. So how do we find out what the velocity of the ion is? Well, we use Fe equals Fb. We know that they cancel off because it's moving, it's not curling upwards or downwards, it's moving straight. So Fe equals Fb, which means Q times E is equal to QVB. But since perpendicular, you can get rid of the vectors, it's just magnitudes. Q's cancel, so V is equal to E over B. And E is 155 volts per meter over 0.0315 Teslas. And so you get a velocity of 4.92 times 10 to the power of 3 meters per second. That's your velocity. Part B, now this electron exits it and gets into another magnetic field, which is perpendicular to the velocity. I'm just going to assume it's into the page again because I like drawing X's on the page. So it's going this way, and then it's going to curve downwards, yes, because magnetic force is still going to be down because they both are into the page. So it's going to be same direction. And so it's going to curl downwards. So what is going to be, it says the radius is 17.5. Okay, so since it's circular, we can say FC is equal to FB, which means mv squared over r is equal to qvb. One of the v's cancel, mv over r. This is just the same thing we did during the content review. Except I have to do it again because you have to show your work on this. It's not an equation that they give you. So it's just a little bit of algebra solving for r. In this case, actually, we don't want to solve for r because we're given the r. Instead, we want to solve for the mass. This is kind of like what I was talking about earlier, where you don't know what element it is, but you know its charge and everything else. And so you use this machine to find out what element it is. So perfect example for that, actually. So you know all these values. Charge is just the value of one electron, which is 1.60 times 10 to the power of negative 19 coulombs. B is 0.0175 Teslas. That's what it tells us. It's this new magnetic field. Radius is 17.5, so 0.175 meters, over velocity, which we calculated to be this. I don't want to write it again. So it's just velocity, that velocity. And so you plug it in, you're going to get 9.96 times 10 to the power of negative 6 kilograms. Which is like a bit, it's like magnitudes of order heavier than like protons and electrons. All right. So that was that. Also not a very hard question. Is just you needed to know exactly how to solve for velocity. If you never heard that that derivation that I showed you in the content review, it's probably going to be a bit hard, but just know how to derive it. A few questions would be like that. Okay, this one's a very simple question. This is one of the easiest questions on here. This is just, you got a magnetic field. It doesn't even tell us the direction because it doesn't matter. So I'm just going to assume it's going this way. And you got a current going through it. Again, direction doesn't matter. It's just the magnitude of the force, but we're assuming they're perpendicular. I mean, it tells us it's perpendicular. And let's see. What is the formula for the force on an electric or a current carrying wire, well, force is just equal to IL cross B, but since they're perpendicular, ILB. I, it says, is 10.8 amps. L, let's see. L is just going to be twice the radius. So it's going to be 2 times 2.5 centimeters. So it's going to be 5 centimeters or 0.05 meters. And B is 0.550 Teslas. That's what it tells us. You just multiply them together and you're going to get FB is equal to 0.297 newtons. And that's your answer. Again, like I told you, very simple. All is just multiplying 3 numbers together. The only tricky part is calculating this length because it doesn't explicitly tell us that. It just tells us the radius. But, yeah. All right, this is where it gets a little bit more tricky, especially number 37 down there. Ooh, that's going to take some time. But number 14 first. This is Biot-Savart because we're given little infinitesimally small portions of wires. And so what can we do? Let's start with this wire. We know that the formula is dB is equal to mu naught over 4 pi times I times dl times cross product r, but we want to just use scalars in this case, so it's sine theta over r squared. So what do we know? I is 12.0 amps. dl is going to be this little segment, so that's going to be 1.5 millimeters or 0.0015 meters. Sine theta, well, what's sine theta? Well, you can just draw a right triangle here, where this is 8 centimeters. This is, what else does it tell us? Oh, they're 5 centimeters apart, so this has to be 2.5 centimeters. And so theta, this is going to be theta because it's just the angle between the current and the radius. So current is this way, radius is that way, and so this is going to be theta. You can use geometry to figure out that's also theta, which means sine is 2.5 over 8. So you just calculate 2.5 over 8. You don't even have to convert to meters because they both are the same unit. And then radius is the physical distance, so that's going to be 8 centimeters or 0.08 meters, and you have to square that, obviously. Mu naught we know is 4 pi times 10 to the negative 7, so 4 pi's cancel is just times 10 to the negative 7. Once you plug everything in, all those values, you just plug it in, you're going to get 8.79 times 10 to the power of negative 8 Teslas, because that's the unit. Well, that's actually not our final answer. That's for the first wire. The second wire is going to be the same thing, except it's 24 amps, so you're just multiplying the current by 2, so it's just going to be exactly twice this. Now, we just want to know if they go in the same direction or if they go in opposite directions. So this one is you hug the pencil with your thumb pointing to the right, and you curl your fingers around, thumb pointing up to the right. So that means it's going to be going into the page there. So axis. For this other one, it's current is going the opposite way. And this time you want your thumbs to point this way, so that so your fingers to point that way, so your thumb points to the left, and that again is into the page because it's going down there. So they both are going in the same direction, which means you add their magnetic fields. So the other one was twice this, so the total magnetic field is just 3 times this value that we got, and so it's going to be equal to 2.64 times 10 to the power of negative 7 Teslas. And that's your answer. All right, not too hard. That's basically how you apply the law of Biot-Savart. It's usually going to give you like these small segments. If it asks you to integrate, it shouldn't, but I'm sure you can do that because you know calculus. It is a calculus-based course. All right, this one's the tricky one because it's the circular loops. The formula for circular loops is a bit different, but let's start with the non-circular part. So let's label this A, this B, and this C. This each of this is a different part of the loop or the wire. So for A, the formula is dB is equal to mu naught over 4 pi times IDL sine theta over r squared, or IDL cross r, the direction of the r vector. So in this case, current is this way. What's our DL? It's also that way. Or they both are in the same direction. Because the point we want is here, so the direction of the radius is that way, current is also that way, or dl basically is that way, which means sine theta is sine of 0, which is 0, so dB is equal to 0. This is for A. And if you look at C, it's going to be the same thing, because current is that way, radius is that way. Again, it's 180 degrees this time, and so sine of 180 is still 0. So for C, dB is still going to be 0. B is what we actually care about. So you could have like conceptualized that A and C would be 0, but you also need to show that, because you can't just say, ha, I'm just looking at the circular portion. You need to prove that the linear portions don't mean anything. Okay, for B, this is the tricky part. The formula is mu naught over, well, okay, there's a few ways you can do it. One is using the formula I told you, but you won't be able to do that on the test. You're going to have to derive the formula. And so let's kind of derive it. First, let's look at the circular portion, where you have the r vector this way and dl that way, because it's direction of the current at a singular point. And so what you can do is find dB for all these points and take the integral of it. So this is actually good, because I wanted to show you an example of using the calculus, like using Biot-Savart and integrating it, which is nice. Okay. So the formula is dB is equal to mu naught over 4 pi. This is just straight Biot-Savart. Times I times dl cross r over r cubed. R cubed, because this r, in this case, we're using r not just as the direction, but the actual vector. So instead of r hat, instead of r hat, it's going to be the r vector, so r cubed. So this also has the length of r, which means we have to divide by r cubed instead of r squared. Now, since the angle between r and dl is going to be 90 degrees, or sine of 90 degrees, which is this, it's going to be 1, which means we don't need the cross product because they're perpendicular to each other. We can just multiply it, which means we don't need the r, so it can just be r squared in the denominator. So yeah, that was a lot of work I just showed you just to simplify it down into a simpler form. But you should know how to do that. You can say these two are perpendicular, so sine of 90 degrees is 1, which means take that out of the equation, is just IDL over r squared. Now, what is dl? Well, that is just a thing you can write at the end, because we're going to integrate it at some point. And so we want to integrate it with respect to L. And so now we basically get mu naught over 4 pi times I over r squared times dl. So now if we integrate both sides, we get b, because integral of db is just b, is equal to, all of this come out because they don't have anything to do with L. So it's just mu naught over 4 pi times I over r squared times integral of dl. Well, integral of dl is just L, kind of like what we did with the integral of db. So you multiply by L. And L, guess what, is going to be 2 pi r, right? Or pi r, because 2 pi r is the entire circumference. Pi r is half the circumference. Because we want the length of the wire, and that's just going to be pi r, because it's a semicircle. So one of the r's canceled, the pi canceled, so we're left with mu naught I over 4r. That's going to be the equation for the magnetic field. We actually found that by integrating it using Biot-Savart. That's for I1. You can do the exact same thing for I2, and you're going to get B is equal to mu naught I2 over 4r. And this is capital R, I apologize. But they're opposite signs, because if you look at this, current is going, let's say, this way, and you put your finger or your thumb around the same direction of the pencil. So it's that way, thumb goes up, and you curl your fingers around. You're going to get into the page down here. In this case, current is still going to the right. You curl your fingers around. This time, you only care about the fingers at the top because the point is above the loop. And so that's going to be going out of the page, because your fingers at the top are going to be out, fingers at the bottom are going to be in. So that means that they're going to be opposite signs, and so you can just do the magnetic field is equal to mu naught over 4r times the absolute value of I1 over I2, because you don't know which one is greater. So that's your equation. And what does your expression give when I1 equals I2? Well, I1 equals I2 means I1 minus I2 is 0, so everything becomes 0, which means the magnetic fields cancel off. So you get B equals 0. So yeah, like I said, that was the tricky one, where you actually had to do some work with calculus and integrate it, but we got there in the end. All right, last question here, which is a bit of Ampere's law, a bit of solenoids, toroids, things like that. So, magnetic field of 37.2 Teslas, and there's 3 different scenarios. One is a long straight wire, 2 is a center of a circular coil of radius 42 centimeters. So that's going to be like a toroid. A circular coil is just a toroid, and the center of a solenoid is a solenoid. So let's start with A. That's going to be a long straight wire, which I gave you an equation for. It's the B is equal to mu naught over 2 pi times I over R, which you can derive from Biot-Savart. Just integrate Biot-Savart for a straight line, which I can actually show you how to do, because we've done some stuff like that before. Mu naught over 4 pi times I times dl over r squared. The reason why I don't care about sine theta is because it's all perpendicular. So sine theta is going to be 1. And if you want to integrate both sides, well, actually, no. This first we have to say it's straight, right? And so you can find like the distance from a segment using r and the length, basically, and you would solve for r in terms of the length, kind of, and that way you'll be able to integrate it and cancel out the length. And so you're going to get just an r in the denominator. It's a little bit more complicated than that. It's going to take a while for me to actually derive the entire thing, but that's the essence of it. You can do the calculus of it, but yeah. And I'm pretty sure this is on the equation sheet, maybe, but you should be able to just write it down and use it. So I would suggest memorizing it. Also, let me erase that. Okay. Where was I? Oh yeah, you use this formula. Mu naught, you know, is 4 pi times 10 to the negative 7. Current is 30, no. Oh, we're trying to find the current. Okay. Radius is 2 centimeters, so that's going to be 0.02 meters. And this is 37.2 Teslas. So you can figure that out, and then you just move everything to one side. You're going to get current is equal to 37.2 times 0.02 divided by whatever this is. It's going to be 2 times 10 to the negative 7. Divide by that. So you're going to get current of 3.72 times 10 to the power of 6 amps as your answer. For B, it's a toroid. So the formula is B is equal to mu naught over, or mu naught times Ni over 2R, basically. If I remember correctly. And you just plug in stuff. So we know mu naught, 4 pi times 10 to the negative 7. We know N is 100 turns. R is 0.42 meters. B is 37.2 again. Again, you just move everything to one side, and so you're going to get a current of 1.24 times 10 to the power 5 amps. These are simple problems in the sense that they're just plug and chug, but it gets you acquainted with the formula, so that's good. Last one is a solenoid. Formula for that is B is equal to mu naught Ni, where N is coils per length, which you can just expand as number of coils over total length times current. So we know this is 37.2 Teslas again. N is 40,000, which is a lot. L is 0.32 meters. Radius, we don't actually care about a radius because there is no radius in the solenoid formula. There is one in the toroid, like I said, but solenoids, it can be anywhere within the solenoid and you're fine. And we know this is 4 pi times 10 to the negative 7. And so you just solve for I by moving everything to one side. You're going to get current of 237 amps. And that's your answer. One thing, these two are big numbers. That's a small number. Why is the solenoid much less than the others? Because it's just 40,000 turns. That's a lot of turns. This thing is 100 turns. This is 40,000. And so there's going to be that huge size. Since the current is inversely proportional to the number of turns, when you increase the number of turns, you're going to decrease the current. And that was our last problem. So that is the end of this video and this unit. So hopefully that helped. Good luck for the test on this and the AP exam, because that's coming up pretty soon too. And I'll see you in our next and last video for all of AP Physics C, electromagnetism. So I'll see you then.